All right, what do we have for solution? What do you need to say about that?
So it's a mixture where the particles are evenly distributed throughout, right?
A homogeneous mixture? So it's a homogeneous mixture of two or more things. So it's usually a liquid. That's usually how we think about it, but it can't be a solid. Alloy would be what we would call that. What's an example of an alloy?
Brass.
So you guys made brass last term by mixing that zinc and that copper together. So that's a homogeneous mixture. All right. How are the solute and the solvent related to each other?
And the solvent is the greatest quantity, and then the solute is the lesser quantity.
Yep. More, less. There really isn't anything else to it. Okay, so what happens to the solubility of a solid as the temperature of the solution decreases? So we've got something like table salt, and it's in water, and the water's getting colder. So what happens to the solubility of that? It decreases. Okay, so why does it go down?
Plus kinetic energy.
Okay. They have less kinetic energy, so it takes more of them to keep an ion solubilized or keep a particle solubilized. Why do they keep doing that? Okay. How about the opposite? I'm going to increase the temperature, but we're now talking about gases. Say again? It also decreases. So why does it also decrease?
Because the gas evaporates faster than the water.
I don't know what you mean by evaporates faster than the water.
It's more volatile.
Not evaporating faster than the water. The water, sure, if it's warming, and it doesn't even need to be warm, it's always evaporating, but the gases itself just leave, right? The result of increasing the kinetic energy of the gas particle is it leaves. It's warm enough to now leave. I don't have any idea what's going on here. There we go. So you can imagine like an O2 inside of a fish bowl, and the O2 reaches the top of the water, or the bottom of the water, reaches the surface of the water, and it's moving so fast that it just leaves the liquid completely. And that doesn't happen if it's colder, because it's not moving so fast that when it reaches the surface, it takes off and goes off into the atmosphere. What do we have for molarity?
Moles of solid divided by liters of solution.
So then its units are moles per liter, and its symbol is a capital M. So basically what we're talking about is the number of particles distributed through a liter of solution. You can think about those things being individual objects inside of there. And they're either crowded together or they're not. What's the concentration reported in units? 140 grams is dissolved in 100 milliliters of solution. Okay, so I've got 140 grams of potassium iodide. I need to turn that into moles. So for every 1 mole of potassium iodide, I've got, what do we got here?
58 or 4, something like that.
All right, 39. 3 plus 126.945. How about 166.003
Really?
grams?
Okay.
And then I'm gonna put my volume unit in the denominator, 100 milliliters, and then I want 1,000 milliliters is 1 liter. All right, and so then my grams of Ki cancels out with my grams of Ki, my milliliters cancels out with my milliliters, and my answer has units of moles per liter, and it's 140 divided by that 166. And so I get 8.4 moles per liter. We're okay with that? Will the potassium iodide all dissolve in 20 degrees Celsius water? What about 10 degrees Celsius? So
Yes, and 20, no, and 10.
yes, and 20, no, and 10. So to answer that question, you're going to need this guy right here. And so I find my 10 degrees and my 20 degrees. So here's my 20 and here's my 10. And so at 20 degrees, I could get 145. And at 10 degrees, I could only get 135. So what was our question? It was 140. So that's a yes at 20 and a no at 10 degrees. Okay, explain how you would make 0.35 molar sodium hydroxide solution. So I need to get a 250 milliliter volumetric flask. Let's start there. And I need to know how many grams of sodium hydroxide to get. So I'm going to say 0.35 moles NaOH per liter. And for every 1 mole NaOH, I need, we've got 22.9898 plus 15.9994 plus 1.00795. 39.9972 grams NaOH. But I'm not making a whole liter, I'm only making 250 milliliters. So 250 milliliters, I need to cancel out that liter unit. So 250 milliliters. And then it's 1,000 milliliters per 1 liter. And so then my moles of NaOH will cancel out, and my milliliters will cancel out, and my liter will cancel out. So the only unit that I have left is grams. And so I've got 0.35 times this 39 number times 250 divided by 1,000. So I get 3.5. So add 3.5 grams of NaOH to flask. 2/3 fill and mix. Fill near line and then fill to line with a dropper. And remember what we're looking for. Let's say this is the neck of my volumetric flask, and this is the laser line that's been drawn. What I need to see is this. That did not change. That's what I'm looking for. The bottom of that little meniscus is hitting the top of that line. And what was the difference between molarity and molality? The molarity is a volume-based unit, and the molality is a mass-based unit. So the good thing about the molarity one is temp independent. Temperature has no effect on it. The con for
The molality one?
I'm sorry, molality. Yeah, I'm pointing towards this molality one. So what's the con of the molality one? If you want to do any volume of any significance, your scale is going to be really expensive. So the scales that we have next door will air out if you hit 135 grams or something like that. So you can't even do 100 milliliters because the flask weighs more than 35 grams. So if I go to put 100 grams of water in there, I've already aired the scale out. And those scales are a little over $400 a piece. So if I want a scale that can read to a few decimal places and can do even something as small as 100 milliliters, I'm spending thousands of dollars. And if I want large volumes, like say 2 or 3 liters, like a 2.5 liter container, I'm probably going to spend like $15,000 on that scale. So it's just cheaper. All right, that's it.